Hello everybody. In this video we are going to look at the language generated by a context-free grammar. So in our previous classes we have already seen how we can define a context-free grammar by using this notation. So G is a grammar, can be denoted by the set of non-terminals, the set of terminals, the set of production rules and the start state. Okay, so this grammar is, you can call this grammar as a generator of a language. Just like we had in case of tokens, the token was generated by the regular expression. Okay, and it was the token, this was the generator, and it was accepted by the finite automata. So for tokens we had the generator was the regular expression and the acceptor was the finite automata. So similarly, in case of languages, of context-free languages, we have the in context-free language. So context-free language is basically the language which is generated by your context-free grammar. So you have a generator, that is your context-free grammar, and you have an acceptor. So what the acceptor does is that this acceptor will tell you, given a string, whether it belongs to that language or not. So in case of context-free languages, the acceptor is a push-down automata. So when we look at parsing, okay, so what we will be doing is we will be given a context-free grammar, and then we have to check whether the strings that we are getting, the tokens that we are, string of tokens that we are getting from the scanner, whether they belong to the language, to that particular language or not. So we have to implement, our parsing is going to be implemented with the help of a push-down automata. So our parsing algorithms are going to construct a push-down automata to find out whether they are going to accept or reject the program. Okay, so let us look at the language generated by a context-free grammar. So we have already discussed about derivation and parse trees. All right. So let's say I'm given a grammar. Let me take an example grammar. I have two non-terminals, S and A. I have two terminals, 0 and 1. Then I have the production rules like this. Let me write the production rules as S derives 0, A or epsilon. And another production rule I have, A derives S1. Okay, so these are my two production rules, and my start state is S. So this is the context-free grammar which is given to us. Okay, now we have to find out what is the language that this grammar generates. Okay, so to do that we will follow the production rules one by one. So I have the production rules. Let me just write down the production rules here. S derives 0A, S derives epsilon, and A derives S1. These are my production rules. Okay, so I will start with the production rule S. So I always have to start any derivation from the start symbol. So when I start with S, I can either pick the first production rule, 1, or I can pick 2. I have an option. Let's say I pick 2. So in that case, what I get is, I get epsilon. So S derives epsilon. So it means that I have this. Let me write my set of strings accepted here. So I put epsilon here because epsilon, the start symbol, can derive epsilon. So after epsilon there is no other option, so I can stop here. So if I use production number 2, I will get epsilon. Now let me say that instead of following production number 2, I pick for production number 1. So in that case, S derives 0A. So I'm using production number 1. I'm just numbering the productions 1, 2, 3. So here I'm using 1. So now I got 0A. Now this is not a string of terminals, so I have to continue. So now 0 is a terminal, it remains as it is. Now I have A. So for A, you can see A matches with production number 3. So I can expand A by S1. So I will replace this A by S1. Okay, so I have used production number 3 to expand A. So now I have 0S1. Alright. Again, now this is not just a string of terminals, so I cannot stop here. So I'll continue. Now again here I have a choice. I have S, I have to expand S now. So I have a choice. So again I can either pick 0 or 1. I can pick 1, production number 1, or production number 2. So again here let me just for clarity, just to explain, let me draw something like this. So suppose here I pick 2 here. In that case I'm replacing S by epsilon. So I will be left with 0, 1. Okay, so 0, 1 is a string of terminal symbols. So 0, 1 is a part of my language, is a string except which belongs to my language. On the other hand, here if I pick 1, production 1, then I will get 0. S will be replaced by 0A. S will be replaced by 0 and A. Okay. And what am I left with? I'm left with the 1 from here. So I have this. So again here I cannot stop. So I continue. Here I apply production number 3 for A. So I get 0, 0. And A I will replace by S1. And already the second S1 is there. So I put a 1 here. So what I got? I got 0, 0, S, 1, 1. So now again I have a choice for S. So I can pick 2 or I can pick 1. If I pick 2, I get 0, 0, 1, 1. So 0, 0, 1, 1 joins my language. Okay. And otherwise I will have 0, 0. And S will be replaced by 0A. So 0A. And I have the 2 1s out here. So this can continue in this manner. Okay. So you will find that the language, this set also continues in this manner. So you will find that a pattern emerges. And what is this pattern? This pattern shows that I am either starting with zeros and I'm ending with ones. Okay? And the number of zeros and the number of ones are equal. So can I write it like this? 0 to the power n and 1 to the power n. So equal number of zeros and 1. And it must start with zeros, it must end with ones. Okay. Now what about the value of n? What should be the value of n? Here you find that number of 0 is 1, number of 1 is also 1. Here it is 2. 2 zeros, 2 ones. But for this, number of zeros and ones is 0. So I can say that for n greater or equal to 0. So I can write it like this, that the language generated by the grammar G is the set of zeros and 1. Okay, 0 to the power n, 1 to the power n. That means that string of length zeros, a string of zeros of length n and string of ones of length n. And n is greater or equal to 0. So this is the language generated by the grammar that we were given. So in this way you can always find out what is the language generated by your grammar. in continuation with this, okay, let us look at the derivation. So suppose I have a string 000111. Okay, now I have to check whether this belongs to my grammar or whether it belongs to my language or not. So we saw two things, that is derivation and parse tree. Parse tree. So if I start with, I have to again start with S. So since this is not epsilon, this is not of length 0, so I will not use the production S, that is production number 2. So I'll use S derives 0A. Okay. Then what we will do? We will expand A. So A will be S1. Okay. Then again, next I have 0, and again S I will expand it using the production. S is 0A. So 0A and the 1 remains. Then again here 0, 0. Again A I will replace it by S1. So I have 2 zeros, 2 1s. Then 0, 0. Then again S I will replace by 0A. 1, 1. Then again A will be replaced by S1. And now I have 3 zeros and 3 1s, so I can stop the derivation process by replacing S by epsilon. So I have used production number 2 and I have terminated here. So this is a derivation. I have used the leftmost derivation here. And for the same thing, I can also have a parse tree. So S 0 A. Then again A will be replaced by S1. Then again S would be replaced by A1. Then this will be replaced by, A will be replaced by, sorry, I missed out something here, I think, 0 A. Then A will be replaced by S1. Then S will be replaced by, 0A. Sorry, this is 0 and this is A. Okay, so this is 0A. Then again A will be replaced by our S1. Okay. Then again S will be replaced by 0A. Alright, then again A will be replaced by S1. Now here S will be replaced by epsilon. So I have, if I traverse this parse tree, the yield, by yield I mean the leaf nodes.